All right, welcome to another MTH218 online class. So this is week number 4. So the biggest thing probably on most people's minds is about the first assignment, which is due this week. So if anyone had any burning questions, I would happily go over them. So if you just haven't been prepared to share yet, just type them in. So ask about assignment 1 if needed. I'll leave the message there for other people if they come in later. So given there's no questions seemingly, I will just go on with a normal part of the class, so to speak. So assignment 1 really matches up to the first part of the subject. And if you may have noticed, there's 3 big parts in that study guide, and assignment 2 covers the second part of the subject. And assignment 3 covers some, but not all of the third part. Why not all of it is because well, it's hard to return it in time if it's due at the very end. So to make sure you get a practice before you get to your final exam, I've put an online assignment, so to speak, for the last one. So something a bit different to what I've done from different years. Just try to get, I'm just conscious of the fact that people really need that practice for that last content. So, but we'll talk about that later. So for the moment, I want to just introduce the second part of the subject. And really, so if you think of the first part, apart from curves and surfaces, was looking at how to extend differentiation. And so looking at key aspects as applications of partial differentiation. So in the second part, let's look at integration, the other side of it. That's the other part of calculus. How can you extend integration to functions of many variables? So we're going to focus on 2 and 3 primarily. So actually mostly 2 for that really. The understanding integration when you've got 2 variables normally is enough to see what the general pattern is. Also, integration often corresponds to dealing with things in real life, and we live in a 3-dimensional world, and so looking integrating over a surface, which is 2D, or over some sort of solid object, which is 3D, are the more natural things to do in a physical context. Methods are useful in more grand scheme of things, of course, too. So that's what we're looking at. So integrating functions over 2 or 3 variables. And the answer is going to be looking at double and triple integrals. So that's pretty much what we're looking at. And so at the heart of all, underneath it all, we've got partial integration. And so what I want to look at, so how it's sort of structured is when you start when you're integrating with one variable, it's just integrating over an interval, one single interval. And there's really not much complexity about that. When you start with 2 or 3, then the region of integration can become much more complex. And so we need to do it slowly. So what I want to do today is just looking at integrating over the simplest regions, which end up being rectangles. And in future weeks, we'll look at integrating over more complex regions. So being not rectangles, but a triangle or a parallelogram or a circle, etc. So, or a completely non-standard shape entirely, which is curve linear, etc. So we'll build up to that, and then we'll look at how to integrate over a solid shape rather than just something 2D. So that's where we're heading towards. So let's look at the 2D stuff. Before we do that, I want to get a sense of partial integration. So we've seen partial differentiation. Partial integration is sort of just the opposite of that. So partial differentiation, if you want to think about it, how you do it, it's really just differentiating a function with respect to one variable, but when you've got lots of other variables in play, and all you really do to them is just assume all the other ones are constant. That's pretty much how you do partial differentiation. So partial integration is the same idea by the integration. So you've got a function of many variables, you integrate the function with respect to just one variable at a time, and when you're doing that, you just assume all the other variables are constant. That's pretty much all it is to it at first glance. There is one or two complicating things, and we'll see that in an example. With partial differentiation, we have a special notation using those little partial things, like you can see in this formula here. So partial z, partial x. within partial integration, there's no special notation. We really just let notation dictate it. So we still use integral signs and differentials, and the differential tells you what you integrate in respect to at a certain time. The main place we'll utilize that in this subject is in terms of double and triple integrals, and the context is abundantly clear. We need to do partial integration because, as you'll see a little bit later down the track, so it'd be very clear what's required. So I want to do an example here, which is a little different to what we're going to do most of the time in the subject. If I can find, okay. So I've got here a partial differential equation. So this is not an ordinary differential equation, it's a partial differential equation because it's an equation with a partial derivative. And what I want to do is I want to find z. So I said, although we're not going to do much of it, we will do this later on when we're trying to find potential functions later on, for example, and the similar sort of things you might see in MTH218 as well. You might see these in other subjects as well. So we've got del z x equals an equation. So what we want to do is, well, z then really is just the partial integral of this function with respect to x. That seems to be the answer. So if the partial derivative is equal to that thing, z is just going to be the integral of it, or the partial integral of it. And you integrate like you expect. So you integrate respect to x. What we're doing is just assuming y is a constant. So the integral of 8 would be 8x. The integral of minus x squared is minus x cubed on 3. The integral of minus 4y squared, well, y is a constant, so it's just you write the constant down, and it's just 1 really. The integral of 1 would be just x. So that's the trickiest part. So that part there, where we're assuming that y is just a constant. Now, when it comes to these sort of integrals, which we won't have to worry about with double integrals very much, we're supposed to put a plus c in the end if it's indefinite. We have to be a little careful. This is the one trick which is worthwhile mentioning here with a partial integral, is this is a constant with respect to what we're integrating with respect to. So we integrate with respect to c, so therefore this plus c is constant with respect to x only. Therefore, in theory, it can be a function of all the other variables around. So all the other variables in this case is, well, just y. So it's constant with respect to x, but not necessarily y. So it's plus a function of y in general. And again, that's the hardest part, I reckon, at least, with doing partial integration, is that you have to worry about when the constant of integration, you have to think of there being functions instead. So that's partial integration. So this last bit, adding the constant integration bit on, we won't have to worry about for a while. So I'll do it again later. The context I'm about to show you in a second, that imply because we're going to be doing definite integrals rather than indefinite ones. So that's the partial integration bit. So pretty straightforward. Okay, so that's how we're going to use it. So what I want to do is I want to consider the idea of a double integral. So let's just take a step back. What do we know already? What do we know how to do? Well, we know how to work out the area under a curve. So the area under a curve, again, so just so you get a curve above the x-axis. We can work out the area of that between different limits. So we can work out that area. And the area ends up being the integral. It's the integral of the function with respect to the variable. So that was a way. And so what this notation means, just to recall, this integral sign is an S, so it's sum. So it's summing up, really, by breaking up this region into lots of different rectangles, is the thought. Each rectangle has a height of fx, and the width of each rectangle is dx, a small amount of x. They're just summing up the area of each rectangle and getting a total area. That's what the notation refers to. Just a good sense to see what the connections are. So the area under curve, simple 1D integral. So what I want to do is I want to consider the area of a volume under a surface. So jumping up a dimension. So here's a little picture of what we can do. So we've got a volume under a surface. What we can do is we can approximate this big solid you'd get by lots of different, well, not rectangles anymore, but lots of rectangular prisms. So this is my little rectangular prisms, heaps of them. And the volume then would be basically summing up the volume of each of these different rectangles. So just looking at one of them in particular, so we've got a nice smooth sort of surface. This is one of the particular rectangles. That's one of them. So just trying to give you a bit of visualization of what it looks like. And so the total volume, I should say, you're just going to be seeing all those sort of things. So putting it, so volume under a surface. So this is just notation for the moment. Is really we want to summing up. That's what we'll put in words. The volume of each individual rectangle. So the height of the rectangle would be the value of the function at a given xy point times by the area of the cross-sectional area, which is probably something small, adding it up. And in short, how we write this down is when we do sums, summing small things, that being integral. But because dA has got an x and a y, we want to sum in both directions. So we write it as a two sign symbols. So the volume, just notation, I haven't said anything. Doesn't really tell you how to work it out yet. Get you worried again. So the volume under a surface is a double integral, so we call it, of a function of two variables, and the differential is dA. So we'll worry about how to work it out in a second. So I'll show you actually talk about in practice how you can work it out. Let's just try to sense the notation. Just try to swallow that down at least, so we can actually understand what it's talking about. Okay. Just get my pictures here. A little bit smaller, maybe. So what I want to do is I want to work out this particular integral here. So it's a double integral, which means summing over 5 with respect to dA. So what this corresponds to is I'm trying to integrate over a certain region. It's given by R, which is just a nice rectangle here. So rectangle where x is between 1 and 3, y is between 2 and 4. So just trying to integrate over a rectangle where the height of the surface itself is just z is equal to 5. So in terms of a picture, that's what it is here. So I've got my x between 1 and 3, y is between 2 and 4, on the bottom axis here, and the surface really is just the same height of 5 everywhere. That's my little picture of what I'm trying to do. So this double integral is just trying to say, let's work out the volume under that surface. All right, let's work out the volume of that particular object there. So my question is, what is that volume? Can you guys tell me what the answer is? What is the volume of that particular solid? So type the answer in. It's fine. So 20 is the answer. Sounds good to me. How you work that out? Well, it's just a rectangular prism, right? And so with a rectangular prism, it's just the all dimensions, so 2 by 2 by the height, which is 5. So 2 times by 2 times by 5. That's sort of how you work it out. So 2 by 2 by 5. So this is a fairly straightforward problem. It's just about decoding what it means. So a double integral, a good way of thinking about it is it's the volume underneath a surface. Now it can be used for other things, just like when you're seeing variable functions of one variable. The integral of one variable can correspond to a volume of revolution, or it could correspond to an area of the curve or a length of a curve. You've seen a few different applications for it, and you'll see double integrals, same things happening. But the classic example, classic interpretation of these things is volume under a surface, and that can help with a few simple cases. But in general, you'll get surfaces which you don't know the answer for directly. You can't just, I know it's rectangular prism, bang, know the answer. So we need to try to find a different way of doing it. So let's just try to give you a sense of what it looks like. So we've got some curved surface. This is my little way of trying to draw my curved surfaces. So it's got a so a bit of a hill sort of is the idea what we're trying to look for. That's on my surface. So the way to work out the volume of this my curved surface here. So this is the basic idea, is cut it up into slices. So let's just draw it in two different ways. So this is the 3D picture, and I'll draw a 2D picture at the same time. 2D is a bit neater. I'm sure you can understand. So the 2D picture really looks at the base, or sometimes you might use the word shadow, of the surface. So you can imagine the shadow, imagine the surface being something up in 3D. The shadow it projects down onto the xy plane, or z equals 0 plane, is the shadow. Or alternatively, you can think of it as being the base. So this is my base, which is just making it into a nice rectangle or square in this instance. So that would be the base here. That's underneath it. So the trick that we've got is to split up this region into different cross sections. So they're cutting up into lots of different bits. So if this is the Z and the X direction, here I'm cutting up, taking slices for fixed Y, for example. I could cut it up into slices of different X's if I wanted to. I mean, they're both acceptable. I'll just pick Y just for my first case. And then with each different slice, you can work out the area of each thing. So let's just try to draw my first slice. I might be looking something like that one. The second one might be another sort of similar shape, but a bit further down. So let's just draw the one on the end here. So the one on the in the end would look something like that. So that would be, so you have lots of, basically, so I've got lots of different slices, and above each slice I've got some sort of solid object sitting above that. And the top of it would be a surface, but I've got steps in it because really I've made sure the edges are parallel just to make it a bit easier. So essentially each of these different slices, so let's take the bottom one here, is really, you've got some sort of area, you've got a thickness to the slice. It's really just I've made them all prisms. The thickness is a small amount of Y. So the small amount of this, the volume of this small little bit here is the area times dy. And so the volume is summing up all these little bits here. And so we've done, and you might have seen this when you did back Maths 101 or something like that, that one way of working out volumes is to cut up into different slices, work at the area of each slice, and just integrate. And indeed, that's what the disk method is, or Washer's method for volumes of revolution. They're really the same idea. It's very much like that. But how do you work out the area? So you go, well, we don't have a nice things based on discs or washers, we've got something more complicated than that. So the area here is a bit more complicated. How would you work at the area? Well, really, the area here, if you think about it, is just the area under this particular curve here. And what's this curve going to be? Well, this curve here really is given by the function f of x, y. That's what it is at every single point in time. But what we've done is we've fixed the y value along here. That's what we've really done. So the area is integrating our function for the change of x. So y is constant for every single different curve. There's lots of curves, so all different y. So the inside area is just the integral of the original function dx. That's just working area under the curve. So what we can see here, and this is the key result, is a volume, when you've got two different variables, would be first you integrate the area. First you integrate the function with respect to one variable, x. That's what we do first, that's the inside. And then when you get an answer, then you integrate that answer with respect to y. And you can see that really is just by sense of splitting up the region into different slices. So showing the formulas. So they're here. So the way to work out the volume, let's make it slightly bigger, say. The way to work out a volume, so a double integral, so it's just saying the volume under a surface of a surface given by z equals fxy, is really about saying, well, I want to split it up as an integral of a function. And really, the way to do it really is to split up into an integral of an integral. That's what it corresponds to. So let me say that again. The best way of doing a double integrals in general is to think of them as being integrals of integrals. And the fancy word for that is called iterated integrals. So as you can see here, I rewrite the dA as a dx dy. We can write it as dy dx. Take your pick. And you do the inside integral first. Always do the inside integral first, and then do the outside. And I'll show what it looks like in practice for an example. You can see that I can take cross sections in terms of x's or y's. I can do either or. And so what the inside is can either be x's, like this first one, or it can be y's, like the second one. You have to take your pick. Often makes no difference whatsoever in terms of the difficulty of the problem. Intermediate calculations will look different, but it looks okay. So let's just try looking at an example of how to do that. So just getting some nice pretty pictures. Now it's gone really, really big. So what I've got here, just to give you a context, I've got a surface that is equal to a minus x squared minus 4y squared, which is an elliptic paraboloid. It's elliptic paraboloid, so upside down. And I've got a base, so given x and y base, which is a nice rectangle, and I want to work out the volume underneath the surface. So in terms of picture, just to get a sense of what we're doing here, that's the elliptic paraboloid, and you can see I've got a nice rectangular base. I'll try and work out the volume of that particular solid. That's what I'm trying to do. So again, things which are helpful, that's the 3D picture. It's good to also have a sense what the 2D picture is. So the 2D picture is integrating over a particular base. So x is between it's between 2 and minus 2. That's the x values we're changing. And integrating between minus 1 and 1. So we're going to be integrating over this particular rectangle. So that's the base or shadow, putting it away, that we're integrating over. So that's the 2D picture. This is the 3D picture. So what we can do is we can take cross sections in terms of x's or y's, take either, and that determines the order of integration. So let's just explain what it looks like analytically. So to work out the volume is the double integral over our rectangle, R for rectangle, of 8 minus x squared minus 4y squared for a particular sort of area. So you write it out in general. In practice, what we're going to do is we're going to integrate with respect to one variable first. And it doesn't really matter which one. In this case, difficulty is pretty much the same. So take your pick. So you can write it as dx, dy, or dy dx, doesn't really matter. I'll tease out examples where it doesn't matter later on. So that's what we're trying to work out. They really are the same thing. So the double integral, I just replace the dA by dx dy. But this is around a few extra things. The dx here refers to the inside. So let's just do colors. So this inside integral matches up to the dx. And it's a definite integral. It's supposed to be, the following thing should be just a number. So I'm going to put numbers on the end here. So maybe you guys can tell me, we're looking at everything. What are the limits for x? What's the smallest x can be and the biggest x can be? So just to get you thinking and at least working your fingers out by typing stuff on. So that's right. So the smallest x can be is -2. The biggest x can be is 2. So it's important that the differential and the limits match up. That's really important. So although you can write dy dx, change the order, it changes the order to write the limits down too. So make sure they match up. Then you can do the outside is a dy, and so the outside limits have to be the limit for y. And again, what are the limits for y? Yep. So -1 to 1. So again, they must match up. So that's a way of writing it down. Now, again, I haven't done much yet, so I haven't really done any work yet at all. I've just written it down. So the real key to doing the problem is to do the inside integral first. That's really the trick. That's it, really. So do the inside integral first, and you go for it. So let's explain. Let's look at what is in practice. So therefore, the outside part is the integral from -1 integrating with respect to y. That does not changing whatsoever. So we're just going to leave it there. Well, we'll do that later. So just the inside. So we're integrating the inside with respect to x. So we did this already. So integrating 8 with respect to x gives you 8x. Integrating x squared gives you minus x cubed on 3. Integrating 4y squared with respect to x gives you -4y squared x. And as you notice, what I'm doing here is I'm doing a partial integral. So I'm integrating with respect to x, assuming y is a constant. That idea of a partial integral before. So that's integrating, and then what you do, you've got limits, is you then sub in the limits. So again, I'd write it down something like that. So I put in square brackets for the limits on the side here. Notice that unlike when I did this example before, I haven't put the constant integration down. And the reason is, well, if I did, I'd just cancel out. So there's no point doing it. And you've seen that when you do different integrals for one variable. So same idea. So I still got to do this evaluate the inside. I haven't finished that off yet. So the outside bit, so -1 to 1 integrating with respect to y, I just leave that. So I haven't done that yet, so I'll just leave it. Just evaluate the inside. So I've got to sub in 2, got to sub in -2. So subbing in 2 gives you 8, 2 gives you 16, minus 2 cubed, 3, -4y squared times by 2 gives you -8y squared. So you notice you get y sticking around. And then minus, subbing in the -2 gives you something really similar. So -16 plus 8 on 3 plus 8y squared. And then you simplify that down. So 16 plus 16 gives you 32. -8 and 3 minus another 8 and 3 gives you -16 on 3. which I can write as one fraction if I wanted to. So whatever that is, so 96, so 80 on 3, plus, so minus 16y squared. If I've made a mistake, just let me know. But pretty much, you just simplify the inside until you get as simple as you can go. The more work you do then, the less work it is to integrate it. So what I've done, just to get to see the picture, is all I've done is integrated the inside, so worked at the inside. And in terms of understanding what it means, this here is the area of a cross section if you make the area of a cross section for a fixed y. So for fixed y, that's the area. So if y is equal to 0, which is the one right in the middle there, then that would be the area of that particular cross section would be 80 on 3. Whereas if you did a cross section of y equals 1, plug in the answer, you get a different answer. So that's just the area of different cross sections. That's what it corresponds to physically if you needed to. In practice, you don't necessarily need to realize that, but it's good just to get a sense of what we're doing here. So you do that on the inside first, and you can see what's reduced down to is this is just a normal one variable integral, which you can do. I hope so. And there's no tricks to it, just integrating per normally. It's an integral from -1 to 1 of an even function, so you can do normal tricks. So you can say, oh, that's twice the integral from 0 to 1 of the original function. So you can do normal things. So this is because it's even. And indeed, I could have done that earlier as well. I mean, I could have used the symmetry because it's even in x to help simplify if I wanted to. So you can do normal tricks that you do for one variable stuff that you know and hopefully like. So then integrate per normally, really is. So what's the integral of 80? What is the integral? Maybe you can do the rest of it. So pull out your piece of paper. What do you reckon the answer is? So integral of 80 on 3. So I encourage you to have a go. I mean, this stuff is what you know. So you get 80 y on 3 minus, you can put the next term in. What's the integral of 16y squared integrating respect to y? Yep, just waiting for Bill's responses. It's good not to leave it too silent. Yep, so you get 16 y cubed on 3, or how you write it down is fine too, from 0 to 1. Sub in the 1, get an answer. Sub in the 0, you get another answer. So sub in the 1, you get 80 on 3 minus 16 on 3. Sub in 0, you get nothing. And again, pulling your calculator, get nice things. So you get 70, 64. So I think the answer is like 128 on 3 is the final answer. I hope so. Again, that part there really is something you should be able to handle yourself, I would hope. So let's just dwell upon what we've done there. The way to do a double integral, so the easiest way is to treat it as an iterated integral, which means do the inside first and then do the outside. And so one extra thing required sometimes is I often write these double integrals in terms of just a generic region, so R over here, and so you have to work out what the limits are. Now, if it's over a rectangle, that's pretty straightforward, but just make sure the limits match up. But really how to do it, inside first, and then do the outside. Now, there are some more tricks as we'll go through it, but that's the main process. Okay, so just the first little trick I want to talk about is the idea of order integration. You can swap the order of integration. So instead of integrating respect to x and then y, you can do the other way around, integrate respect to y, then x. Now for rectangles, that's pretty straightforward. That picture doesn't come out properly. It's okay. for rectangles, that's pretty straightforward. For other things, it's not so straightforward, but we'll come to that later. Got this, write this question out properly. What I want to do is I want to do this double integral. And you can see integral from 0 to 0.5, 0 to pi. So it's the x is going from 0 to 0.5, the y is going from 0 to pi, and we're integrating, so working out the volume under this particular surface, which looks a bit more complicated. So let's try to show a picture of what it looks like. So that's the picture of the curve. That's a picture of the surface, and it's been filled in. So that's what we're trying to work out, the volume under that particular surface. So something a bit more non-standard. Trying to work out the volume under that particular surface there. So it's been written down as an integral of the inside and the outside. So you can just go, let's try working out directly. You go, well, so the direct approach would be to work out the inside integral first. That's the basic idea. So with this inside integral, if you have to integrate this with respect to x, you've got to integrate y cos a constant y. And go, well, that's a product of y and cos of y. And therefore, to integrate product like that, you're really going to have to do integration by parts. So if you did the inside integral, you could do it. I want to make that clear that it is doable. But in the process of doing that, you'd have to use integration by parts. Indeed, not sure much you remember, you have to integration by parts twice to actually resolve the answer. And in the process, you're getting 1 on x's cropping up, which will end up being problematic when you've got x being 0. So you could do it, but you'd end up taking a bit more time to do it, take a bit of time. And secondly, you'd end up getting 1 x, so you get improper integrals the second time round, which again, you could handle, but it all sounds really hard. I guess is the way to do it. So you go, well, can I make it easier? Can I just change things around? You go, well, if I integrate with respect to x first, that's easier to integrate with respect to x. Pretty much easier. So let's just swap the orders of it. Let's just swap the integral around. So what I'm going to do, instead of integrating with respect to y first, let's integrate with respect to x first. Now, for rectangles, the transformation's easy. Basically, the inside integral now becomes the limits for x, and the outside integral becomes the limits for y. So you can see all I'm really doing for the moment is just swapping these two around. Now, for more complicated regions, it's more complicated to do that. Like it requires a bit more effort. But you might want to do it for the same sorts of reasons. And even if it was not a rectangle but something more complicated, trying to integrate by parts first just doesn't sound like fun when the other one's much easier. So even though it would be a lot more effort for a general region, I would still do it. So this swap in the order of integration is a good sort of good arrow you can have in your, so a good little technique you can apply. So then once you've got that, now we've got an integral, we're just going to do inside integral first. And because we're integrating with respect to x, it's an easier problem to do. Well, at least I think so. You can check it out yourself, and you can try both ways yourself. I'll just do one, and you can let me know if you think what you think's the best way. So the outside bit sticks around, so not really doing anything. So we're just doing the inside. So we're integrating this inside function. So it might be easier to zoom in on that. That's really zoomed in. Just trying to think of how to do this. This is just the inside part. So we're integrating this with respect to x. Now, depending on your skills with integration, you might just be able to write down the answer. I encourage you to do that. I mean, I just encourage you to go bang on. That's the answer. But you may not be able to. So let's just look at it. So does anyone know what the indefinite integral for that is? If you don't know, what method would you try to do for integrating it? And that's what I'm coming to do. We've got a way to solve it. So as Mark's got, he's going, oh, bang, I can see that's just reverse chain rule and go for that. So that's one way of doing it, which I presume how Mark's did it. So you can say, oh, let's reverse chain rule. If you can't see that, so the slow method, which I'll do because it might help, is you go, well, this is a function of a function, so cos of x, y, and so you might want to do substitution. So I might want to let u equals x, y, and then you have to do, and then if it's really a partial integral, put an equal sign in here. And so the standard thing with substitution, you go du dx. I should make them partials because that's really technically what they're doing. So partial derivative of u respect to x is going to be y. And so you can rearrange it as the dx thing is equal to du on y. And if you want to change limits, Mark's approach is quicker. But let's write it down. So if x is 0 and x is 0.5, then u is x times y, so 0 or a half times y, so y on 2, shall we call it? So just plug in. So this is what you do for a substitution method. So inside integral, if you're doing substitution, the integral from 0 to y on 2 of y cos xy, which is calling u, dx. So plugging this bit in to u and y. So I really just done substitution. And you can see the beauty of it, all the y's cancel out, which is why it was a nice thing to do. And you get the answer of cos u du. The integral of that would give you minus sine u, or as I put it, minus sine xy, essentially what it is. And we want to substitute the limits of u being 0 and u being 1 and 2. So you plug the limits in, plugging in minus 1 and 2 gives you minus sine 1 and 2, plugging in 0 gives you nothing. So I can leave it out. So just wanted to take a step back. I'm just trying to work out the inside integral. That's really what I'm trying to do. So just trying to show you that you can use any technique of integration that you already know. So partial fractions, parts, or as you can see, reverse chain rule is the quickest way of doing this one. Or if you can't see reverse chain rule, doing substitution. I certainly encourage reverse chain rule. Makes this much quicker problem, much easier to do. So I'd encourage that if you can. But you're allowed to use all those other powerful techniques you've got at your disposal if you need to. And if you're going through that, going, wow, scratching your head, I can't remember parts or whatever it might be. If you can't remember some of these methods, please revise them as you need to, as it crops up. So you're going, oh, substitution, that rings bells. Look it up. Go back. The textbook covers them all the methods. Have a look and make sure you've practiced those things. If you need help, speak to me by all means. But you do need, as you can see, those methods need to start becoming a little bit more second nature so you can do them all in one bigger part of a bigger problem. So after what we're doing here, so just look at the big picture, doing the inside integral gives you the minus sine y on 2. So you do all the inside bit, just gives you this thing, which looks a bit more straightforward. And once you've done the inside, you just do the outside. It's the same approach. And again, it's a function of function. So again, you can do substitution if you need to. I'll do it use reverse chain rule, which is still my preferred method of doing it. So you got a function of function. So reverse chain rule, as long as the inside is linear respect to y, it's okay. So integral of minus sine gives you minus cos. But then I have to divide by the partial derivative of y, partial derivative of the inside with respect to the variable y. So I have to divide by a half, which means the cross dividing by a half is equal to multiplying by 2. That's my quick way of writing it down. So I hope you caught that. So that's just reverse chain rule. And then I wanted to integrate that between y0 up to pi. So you sub in pi, eating minus 2 cos pi on 2. Minus chucking in 0. So minus is 2 cos of 0. The pi and 2, cos of pi and 2, can you remember what cos of pi and 2 is equal to? These ones are useful to remember. If you don't remember it, you can always pull out your calculator. So it's 0, that's right, that's 0. What's cos of 0? That's 1. So you get 0 plus 2, and so therefore the final answer is 2. So, I mean, more people were happy to write down the answer, so thank you, but it's good to remember these things. And again, people at different levels, all right? So let's be honest about here. So how much you remember some of that prerequisite stuff does vary a bit. But the new stuff is this double integral. The main idea, just recapping, making it really clear, to do double integrals, you write it as an inside and outside integral. You do the inside first and then the outside. They're just an integral. It's a partial integral, but it's integral. And so any tricks that you know, you can apply. You're allowed to use them. Make it as easy as you possibly can. One extra trick, so the extra trick really for it, is you're allowed to swap the order of integration. And that can be helpful to make problems easier to do. Now, in this case, the original, as it was originally written, you could have done it. It makes it harder, but you could have done it. Sometimes, if you don't swap the order of integral, it becomes vastly harder if you don't swap it. So much so you have to jump into non-elementary functions, which never sounds like fun. So swapping order of integration is a very useful technique at times. So that's the primary stuff I want to mention for rectangular ones. So what I've really done here, I'm sure I'll answer some questions in a second, but really introduce the idea of a double integral. So that is integrating two variables at once, and the main application for the moment is working at volumes under a surface. Now, usual things apply. So function of one variable is an area under the curve. Now, it's really the signed area, and therefore there's tricks if it goes up, above, and below. Same thing here with volumes. It's really a signed volume, technically speaking. We'll do other applications a bit later on. But how the subject proceeds is looking at how to do these double integrals. So have a practice. You need to get your head around it, what it really works, and you might need to revise some integration methods as you're doing it. So the next complication is how do you integrate over other sorts of regions, and so we'll look at that more next week. Assignment 1 due really soon, so I'll leave it there just for the moment. So one other thing I can talk about is how you do some of this stuff in Maple, so I can do that if necessary. But before I proceed, I just want to make sure if you guys have any other questions that you want to answer, which can be about what I did now, or can be about anything previous in your subject or whatnot, or bigger questions. So does any of you guys have any other questions that you'd like me to address before I just talk about Maple? Okay, here's a question. Yep, I'll just wait for it to come through. Okay, nothing, that's fine. Okay, so just a quick discussion of Maple here. Let's make it a bit bigger. So these double integrals you can do in Maple, just not directly. And so you have to use a package called vector calculus. So do with vector calculus just puts the package in. So you have to type that in first. So I just type in the chat box. So if people are already looking at this slide, they can see the words more clearly copy and paste. So that's how you do it. And then it's integral. So when you do it with vector calculus, it redefines integral command to do other fancy stuff. So to do that last one, I can see it up top there, but it's basically top the function in. So I'm integrating y equals cos x times by y. Then you type the variables you want in square brackets. So the variables are x and y. That's what we integrate respect to. So x and then y. And then you have to specify the region you're integrating over. And so Maple can handle various types of regions, including circles and polygons and various things. So we'll keep it simple, just do rectangle. So the rectangle, pretty much, you have to, because we'll specify x first, I have to give the elements for x first. So the limits for x was 0 up to 0.5, and the y limits were from 0 up to pi. And then close brackets, semicolon, and press enter, and it gives you the answer. And I'm not sure if you can see it, but it gives you the answer of 2 just there. So we're going to do rectangles just for a little while. In general, if I remember the words properly, I'll just test it out. The word, what will tend to do more generic regions, and so therefore the word that you will use more commonly for later weeks is word region. So region is just limits for x and y, a bit more general. Now, for the moment, it doesn't look any different. But these things here would be the limits you'd have on the integrals that it corresponds to. And indeed, you can swap the orders of integral. You can swap the order of integration. So if I could do y and x first, so I can just do swap the order of integration by swapping the orders, and you can see the answers 2 the same. You get the same answer both times. So just copy some of these things down. So these are always to check your answer, right? You can do other things to see what it looks like. If you just do a comma and then inert, the word inert. Let's bump it up so you can get a chance of seeing it. So look at the difference between these two. So you can see in these two cases here that how you specify it as x comma y or y comma x. Does the integral either as the y dx or dx dy. It can do either or. And so the inert form just shows you how it understands what you've typed in. So it doesn't actually do any evaluation. It just shows you what it looks like in notation. And that's just a good way of just checking you've typed it in properly, if nothing else. Right? So it's just a way of checking type it in properly, and then you get rid of the inert to get the answer. You can type the integrals in individually to check intermediate work. So that's helpful. So part 2, there's lots of stuff. There's the sections towards the end of part 2 are, I guess, more like appendices. And one of them mentions a bit more about Maple. So some of the instructions are there. If you want it, you might find it more useful later on rather than right now. But just flagging it while we have some time. And you can see you got the answer 2, which is what we worked out directly as well. So again, it's useful just to have confirmation that you're on the right track. Now, for your tutorials and textbook, the answers are there. But if you're in an assignment, that might be a useful way of just making sure you're on the right track for your assignment. So I'll leave it there today, if that's okay, unless you've got thought of a question right now. So thank you very much for sticking through it. And we'll look at more general regions next week. But Maple is really good just for the visualization and stuff like that. And so I'll put the notes up, which has the Maple commands as well when I put the recording up, if that's helpful for people. Cool. So thank you very much, everybody. And I'll see you next week. So have a good Easter.